All right, so in this example, we're asked, or we're told that phosphorus and sulfur form a series of binary compounds. And the base that are characterized are those three. All of them melt congruently, and then we must assume that only those three binary compounds exist. And then we're asked to draw a schematic phase diagram for them. We're given some information, and then also draw a schematic cooling curve for one of the compositions. We're given some information about an eutectic that we must take into consideration. Okay, so I've just drawn a little thing that we're going to play with here. But before we start with that, there's some things that we need to consider. So the first thing is we're given some information about the compounds. So for each of these compounds, right, they have their molecular formulas. So we were given the molecular formulas. In other words, we can figure out where on the phase diagram they must exist. So where their lines must exist. And to do that, we can calculate their mole fraction. So the mole fraction of the sulfur in each of them. So that's just a simple like grade 2 calculation. So in other words, it's if we write a general formula such as PNSM. So in other words, you know these numbers. So it's P is the N number and S is the M number. Then it is M times the molar mass of sulfur divided by M times the molar mass of sulfur plus N times the molar mass of phosphorus will give us the mole fraction of sulfur in the compound. If it were like normally we use AB, then you can just say the numbers. So if we had, for example, let me just write it down here. So if we had AB2, we would have just said the mole fraction of A would be 1 over 1 plus 2, that is equal to a third, right? So technically what that implies is that is the 1 times the molar mass of A, 1 times the molar mass of A, 2 times the molar mass of B. But because we assume A and B are unimolecular, we don't always write that. So, but in this case, phosphorus and sulfur aren't unimolecular, so we can't do that. So they have different molar masses, so we have to take that into consideration when we calculate that. Okay, so that basically comes down to something that is M times 32.06 over M times 32.06 plus N times 30.97. Therefore, it's gram per mole. And then if you plug that in for each of them, for P4S3, you get a value of 0.44 equals to the mole fraction. For P4S7, you get a value of 0.64, and for P4S10, we get a value of 0.72. Okay, so we know at these three compositions, we're going to have congruent melting compounds. So what we can immediately do, of course, I can also say, I quickly looked it up. This one has the highest melting point of the three, so it has the highest. So this one is the lowest. Highest. And then so this is the median. Okay. And because we're doing it schematically, it doesn't really matter what it is. So on our phase diagram, we have a 0 and a 0. This is 0.5 there, 0.25 there, 0.75 is there. So we know these are line compounds, right? So we're going to have at 0.44, so let's say that's around about there. We're going to have a line compound that does something like that. So line compound for P4S3, and then at 0.64, which is there, is going to be the one with the highest melting temperature. Oh, that's a terrible line. One of the highest melting temperature. So just draw it like that. So that's P4S7. It's going to be there. And then 0.72, so the one in the middle. So sort of like there. So it's in the middle of those two. Then that's P4S10. It's around about there. Okay. So we know that is our starting point for our diagram, because we know they're congruently melting, so we know the shape around them is going to be like that. We don't have to look for the T shape for incongruent melting. Okay, but let's use some other information that we also are provided with. Then we're also given of course, the melting points of sulfur and phosphorus. So the pure melting point of phosphorus, we're plotting this against sulfur. So at 1 sulfur, so in other words, the highest melting point must be here on the right-hand side. So the highest melting point, it will be less than any of these binary compounds. So say around about there, we expect a melting point. And this one must be lower than that melting point. So we say it's going to be there. That one will be for the phosphorus. Okay. And then, because we know, we have these line compounds and whatever, we expect eutectics to be present in between each of these. I don't know really where in between them. That's not specified. So you can just make them up if they're not specified. So that's not that important. You maybe just not at the same temperature. Just ensure that they're at different temperatures. Right. So that's how we're going to build them. So let me draw. So in other words, we start at this temperature. We go to an eutectic. I think they're actually given the B part that this one needs to be at 0.2. So I think 0.2 is around about there. So let's define that one. So this one needs to go to 0.2. Then it needs to, let's make them all in the middle of these points. Okay, so this one, then just connect the dots. Congruently melting, so it has to go over the peak, over there, and over there. Right, and there we have a very rough looking phase diagram for our situation. You can, of course, now add here roughly, so that's 44 degrees Celsius. This is 119, I think I said. 119 degrees Celsius. I'll place a nice one in the notes that's sort of more directly made, corresponding to things. But you can, if depending on the amount of information given, you can of course be more specific, less specific, whatever. Okay, so now we're left with having to sort of figure out what the regions are. So we of course have a liquid region on top here. We have a bunch of solid regions we can immediately identify. Okay, we call them solid 1, 2, 3, 4 because we'll discuss what they are just now. And then we have a bunch of solid liquid regions. Let's call them T1, T2, T3, T4, T5, T6, T7, and T8. Okay. So, I think this was quite straightforward. If they're congruently melting, you expect there should be an eutectic in between any congruently melting points. Yeah, that's kind of straightforward to do. Now, the more difficult part is figuring out what should be in all these phases. So let's write, so at L, what do we expect in the liquid phase? Well, in the liquid phase, technically anything can be liquid. I mean, we have congruently melting points, so we can expect any liquid really. Yeah, so really any liquid, but we can say we expect liquid, solid, and oh, that's a very bad ampersand, but anyway, liquid and solid phosphorus, or liquid phosphorus and sulfur, at least. We don't have enough information really about the compounds to say anything, but I mean, in principle, we should, because it's congruent melting, we can expect to see any of the binary compounds in the liquid phase as well. So you can stop because there's not a lot of information given. You can just say this is a liquid phase. That's also good enough, but you can say it's liquid and solid. Our S1 region, if we look where it is located, so it's located to the left of the P4S3 region. So that should imply that it is in the phosphorus-rich region. So it should contain solid phosphorus, so solid phosphorus plus then, of course, solid P4S3, right? That's what we expect. Say, then we move to the S2 region. This is now to the right of our binary compound, but it's to the left of our second binary compound. So it should be a mixture of those two binary compounds. So it will be solid mixture of P4S3 plus P4S7. And then the same for the second or the third solid region. We expect a mixture of P4S7 plus P4S10, right? And then finally, for the fourth solid region, we expect, again, because we're now in the sulfur-rich region, we're to the right of the last binary compound. So we expect solid P4S10, but with solid sulfur. So let's just say solid sulfur to make the distinction. Yeah, so that's what we expect in the solid regions. Remember, so we start off with solid phosphorus, and then there's not enough sulfur to be on its own, so that reacts with the excess phosphorus to form the first binary compound. And then in between, we have the mixtures of the binary compounds, or if there's just one binary compound, then you usually have you don't have a mixture because you just have the line. And then when you have the switch over between which one is in excess, then it becomes the one comes trapped in the binary compound, and the other one becomes in excess, which is then S4. Right, so that is what you see here. Okay, and a bit more difficult regions is, of course, the T regions. So T1, let's just look where T1 is. So T1 is our first solid liquid region. So it is in our phosphorus-rich region. So we know we have solid phosphorus. There will be solid phosphorus because it's just below the melting point of phosphorus, but there's also going to be liquid. And that might be, that liquid might be liquid P4S3, it could be liquid phosphorus, it could be liquid sulfur, some combination. So you don't have to be too specific with what you say. So it could be, in other words, P4S3 plus P plus S liquid. Okay. Then T2. T2 is to the left of our first binary compound. So we then expect solid binary compound to be there. So solid P4S3 plus liquid phosphorus and sulfur. Right? Then where's T3? T3 is to the right of our first binary compound. So we still expect it to be solid binary compound plus liquid, solid, and sulfur. Liquid, phosphorus, and sulfur, my apologies. Okay, T4, going to be to the left of our second binary compound. You sort of see the pattern, so I mean, I don't want to page back the same way all the time. We're just going to write it quickly and then we'll go back and explain it. So P4 is 7 plus liquid P plus S. So that was for T4 and T5, yeah? T4 and T5. So T4 and T5 is opposite sides of P4S7. So T4, so that means we have liquid phosphorus and sulfur, which can form solid P4S7, which crystallizes there. It's below the melting point of it. Anyway, so then the same goes for T6 and T7. What do we expect? It's to the left and the right of the line compound P4, so P4S10, so we will have solid, solid P4S10, right, plus liquid phosphorus and sulfur. Okay. And then just finally, T8. What is T8? T8, of course, is the region where we have excess sulfur. So we expect there to be solid sulfur present, plus a liquid. And that liquid, you don't have to necessarily specify, but we could expect it to be liquid P4S10 because it's the last binary compound that was formed. So it could be that plus liquid phosphorus plus liquid sulfur because it's around about at its melting point. It's way beyond the melting point of phosphorus. So whatever phosphorus will be there will be definitely melted. Okay, so that is how you build a binary phase diagram. Of course, given if you have more and more information, the more specific you can be about the phase diagram. If you have specific information about geotactics, then you can make them specific at specific points. If you're given incongruent points, you can handle them. Okay. Now we just have to do the cooling curve. So I'm going to draw the cooling curve here next to it. We have to do it for a composition of 0.3. So 0.3 is around about here. So let's say that's here. So if we have something that cools at 0.3, there's basically, it seems like, two major important points. It's that point and this point, the eutectic itself. Okay, so what happens at this point? At this point, we'll see a slowing of the rate of cooling. So in other words, we're going to see our system cools. Oh my word. Our system is going to cool down. And at this point, it's going to change the rate of cooling. Let me just get this better. It's going to cool down, and at that temperature, it's going to change the rate of cooling. So in other words, there's a kink in our diagram. You can indicate it with a line. You can call this point alpha on your diagram, or you can go call that point alpha, or whatever you want to call it. But there is a change in the rate. Change in rate. Why? Because this is a temperature versus time diagram. So in other words, we're plotting here dt versus dt. And then, so if you have a change in the gradient, you're going to have a change in dt dt. So that means there's a change in the rate. And then at the eutectic, we expect a plateau. And then afterwards, there should be another cooling once you get to the solid phase. Because here we have because we go from liquid phase to liquid plus solid phase, which is equal to T2. And then here, again, we have only a solid phase, which is equal to S1. So, and when you have a pure liquid, then in the liquid plus solid phase, we have some crystallization of some solid, but also some liquid still. So that's why we have a change in the rate of cooling. And then we have the eutectic, where it slows, where everything, all the phases change to solid phase, and then everything is in a solid phase. And then we have a uniform change or rate of cooling again in the solid phase, all the way down to whatever room temperature is, where it will remain constant again later on. But we don't show that in the diagram. So I think we can call that, I called it alpha, but I mean, you can call it B1. Sometimes it's called B1. I think that's the use sometimes. And then, of course, we can call these eutectics E1, E2, E3, and E4. So then we can call this point E1. Yeah, so that is quite useful. Okay. And it occurs at around about 20 degrees Celsius, if you want to be specific. And B1 is at approximately 125 degrees Celsius. I know it doesn't look like that because my diagram is not to scale, not at all, but it's the effort that counts, you know. You get I'm sure you get the gist of it. Okay, so I think it's a nice question. You probably will never get something as complex as this, but it's actually just to show you that it's relatively straightforward to draw even something that might seem very complex at first. Of course, the more, and even with a relatively little information, the more information you get might more confuse you, but you don't need that much information to just start doing it. All right, so I hope this was useful in explaining some of the concepts, especially perhaps the congruently melting part of it. Now you've seen it in a diagram, you've gone from just the concept to putting it into a diagram yourself. And yeah, that's example 4.5.